Hello, Western Australia. Welcome. This is the final of our TI-inspired WACE exam preparation series for mathematics methods for 2016. And well done to all of you, whether you've been watching us live and being able to participate live with questions and answers as we go, or whether you've been watching the recorded YouTube clip at a later stage. We certainly hope that this review series has been of benefit to you as you move towards your exams. So to round off the series this afternoon, you can see sampling, interval estimates for proportions, and this is the part of the course that I know when I've been teaching it, it's usually been taught at the end of the course, and it's one that I think is still one where students can quite often pick up some easier marks, I think, if they get a grip of the main ideas in this. It is definitely a topic where understanding the features of your calculator will greatly assist you, and some of the little wizards and tricks that are on your calculator for this. So without further ado, I will thank for the last time for our series and hand over to you, your teacher, who has done a fantastic job in preparing and delivering this program for you, Mr. Stephen Julian. How are you going, Stephen?
Thank you, Brian. How are you? And good evening, everyone. Thank you, Brian. Yeah, we'll just get...
Going well here, mate.
Yep, good. Yeah, finally got some... Sorry?
We're actually on school holidays over this end of the show.
Oh, very good. Yeah, 1 week to go for our guys, although a lot of the Year 12s will have had or will have mocks more than likely during their holidays. So we won't call it a holiday for them. We'll call it more of a study program. But, I know there's a lot of them who will be involved. I've got a group of mine coming in next Monday, so I know a lot going on. Now, I've shared my desktop here, Brian. I'm just not sure you're seeing anything at your end.
I can see it's coming along. It's looking fairly dark at this stage.
Yep. Okay. Let's just see. Yeah, even I'm not seeing a lot on my computer. So
our brains trusted MBC are online. Good afternoon to those again.
Very good. Okay, just bear with us, people. Just trying to work out why we might not have anything appearing here.
Did you switch the lights out? Here we go. That's looking good.
We've had another blackout in Mandurah, I think, Brian. Is that now appearing?
That's looking very good.
Looking pretty good at your end. Good. Okay. We'll now make sure. I did just pay the power bill today, so I'm glad they've just finally processed it for us. Okay. Anyway, without any more delay, as Brian said, tonight we're looking at sampling, and just being our last session and wrapping up, we'll probably have a look at a couple other things towards the end. So this can be a fairly heavy topic and something that probably don't want to rush too much through. So I'm going to give you a couple of ideas of where you can find some further clarification and some explanations of some of the things we're using. Being a 50-minute roughly session, obviously there's a fair bit that I can't get through, so hopefully a couple of the other resources I give you tonight will help you. And you should have hopefully seen on the Google Share Drive, there should be the PowerPoint for tonight again, which is what I'll be working through. And there's also a TNS file on there for sampling, which I'll spend a little bit of time on. It was very kindly given to me by a gentleman called Frank Moyer, who's a maths teacher over in Victoria. And we'll spend a little bit of time going through that and just see the power of his TNS file. So let's get into it. No need to go too much more into that tonight. So the first couple of slides we've sort of discussed a little bit. I guess tonight, last week we looked at the probability idea. Tonight we want to spend a little bit more time talking about sampling, so the use of some of these random number generators. So I just want to spend probably the first 5 minutes just talking about how we can generate things using the random number generator. My students often say to me, oh, well, if we've got random numbers, can we just make them up? Well, sometimes in the exam they will ask you to justify and explain how you're using your technology to come up with these numbers. So the syntax is important. Obviously, there's various ways that you can do that. So we're going to start with a screen. So I'm over here on my calculator. I'm going into a new document. And what I want to do is I want to generate some numbers. So I'm going to go into an add calculator, and we're going to randomly generate some numbers. But something you may have seen a few times, and this is this seed idea down the bottom, that when you're in class, the numbers that are coming up on the screen might not be necessarily that random. Being very much a computer and based on different algorithms and things like that, it's important that if you really genuinely want a random set of numbers that look random anyway, that you actually do this rand seed process. So we go into menu, under probability, and you'll notice in random, at the very bottom here, number 6, there's this seed idea. Now what I suggest when I do it with my students is to put in the last 4 digits of your telephone number. It's not a bad idea. I won't give too much more away about mine. So 3683.
No, well, your bank card.
Yeah, thanks. Actually, I'm quite happy with that, Brian. You can pay all my debts off. That would be very nice of you. So 3683. And if we do that, you'll actually find that it'll reset based on the algorithm. It'll set it at a new point, so you are at least looking like you're being a bit random with your numbers. Okay, so a couple of ones I just wanted to touch upon. The first one is just to get a random normal number, so menu. And if we go into probability, random, and number 1. Now, if I just press enter, what I'll get is a number between 0 and 1. Now, you'll notice that mine's fairly short here at the moment. Part of the reason for that is in doc, under settings and status, and in the document setting, I've actually got mine set to float 2. So I'm trying to keep these numbers fairly small. If we want to see a little bit more detail, then I might go to float 4 and use that so we can see a few more numbers. Just, I guess it depends on what the situation is and what the exam's after. So if I just go back up, highlight that, and press return, you'll see now I'm seeing a little bit more detail. And I can just keep pressing return to get individual numbers if I want to do it that way. If I want to be a bit quicker and I don't want to have to do that each time and I want a list of numbers, I can go probability, random, number, and maybe I want 3 numbers. So rand 3, and you'll see that it generates 3 numbers for me nice and quickly. But what happens if we want a set of scores that are between, say, 5 and 6? Well, I can go up. I might just keep using my rand 3. Rather than starting with 0 to 1, which is what the rand is generating as a decimal, we could start it as being 5 to 6 by adding 5. And suddenly you'll notice that you'll get a series of random numbers that range from 5 to 6, and again, depending on the accuracy, you can put it as being float 3, 4, 5, whatever you feel is necessary. What about if we want to actually make the range bigger than just 5 to 6? Well, we can do that as well. So menu, probability, random. We're going to do a number, and again, let's make it 3 of them. We want to perhaps make it 10 as being, be 10 as being your domain or the width of your values that you want to get. So times 10, and then again, we might want to start, let's make it 20 this time. So we want numbers from 20 to 30, and we want 3 of them. If I press enter, you'll notice there that straight away we're getting numbers between 20 and 30, and we've got 3 of them at a time. That's obviously very useful. There is a way of getting around it if you want random integers, but at the moment this is just a nice way if you want to generate things like measurements, if they ask you to generate money, etc., etc. This little process works really, really nicely. Okay, what about if we do want to have random integers rather than whole numbers? Well, we could fiddle around with our float, or we can go up to menu, probability, random, and our next option is rand int. Now, rand int, this one has a little bit of different syntax, and this week, just showing you, again, this catalogue button idea. If I push this, press the letter R, it'll take you to the start of the random options, or the R options. I'm looking at a random integer, and it's telling me here that I want a lower boundary, an upper boundary, and if I do want more than just one number, how many of them do I want? So coming back in, let's say I want the numbers 0 to 10, and I want 5 of them, and again, we're doing random integers. There's our numbers, 4, 9, 0, 4, 6. Gives us a nice little display of values, and again, you can make that as many as you want. The next one that we could possibly look at is random binomial. Again, it's going to become very important for us later tonight. So random binomial. Now, again, in your catalogue, if we just go down a couple, up a couple, we want the number of trials, or the n value, our probability of success, and how many of these numbers that we want to generate. So let's make it 10, probability of success of 0.2, and let's say we want to generate 5 of those trials. And because we've got 0.2, we would probably expect our values to be around the 2, 3, 1 mark, just based on the probability of success there. This saying that we'd expect this is a trial with 3 successes out of 10, 3 successes out of 10, 3 successes out of 10, 2 and 3. The next one we can generate is the normal distribution. So random normal. Now, the syntax here, I won't go into the template, but it's our mu, our mean, our standard deviation, and again, whether we want multiple trials of those. And again, we should start finding that those numbers are going to hover 1 standard deviation, 2 standard deviations either side of 10, depending on, again, the amount of numbers that we generate. Again, we do see a few dropping down into our lower tail, and we'd expect that to happen, but a nice little quick generation of those numbers. Now, one that people probably haven't played around with very much is this next one, which is random sample. Now, again, not a bad one if you've been given a set of numbers and you have to generate a sample from there and you don't want to spend time in the exam trying to make things up too much. So I'm going to Control-I and insert a list and spreadsheet. At the very top, I'm going to call it X for a name, and I'm just going to put 1, 2, 3, 4, 5. Okay, so we have our numbers 1 through to 5, and what we want to do here is I want to draw a random sample from those numbers. Now, in this case, obviously, I could have just used random integers between 1 and 5. You could actually use skewed data, so you could actually put in things where there's a leaning towards one end of the values compared to the other. I'm going to go back into 1.1. I'm going to go into menu, and I'm going to go into probability, random, sample, and in random sample, the first part of the syntax is which list I'm going to take that from. So in var, if I push the var key just above 9, you notice it gives me the option that X is the list I want to take it from. The number of trials. Now, in this case, I have 5 numbers there, so if I put in, say, 10, let's have a look at what happens. Yeah, it's okay with that. It's actually coping with the fact that it's doing it with replacement, so it can pull more than one number out once, so it's multiple draws of that same number. If I go into random and seed and put X, comma, wrong one, rand samp, not rand seed, probability, random, sample, and if I go X, comma, 10, now if I put comma 1 on the end, what comma 1 means at the end is I'm doing it with no replacement. So if I press enter, it'll suddenly say, oops, I've run out of data because I can't draw 10 numbers from 5. So obviously, because I've only put 5 numbers in, I would need to change that to be a number smaller than 5. So let's make it 4. And now it can cope with it without having any replacement. So again, the X is the column title from our spreadsheet, telling us how many of those numbers we want to draw out. If you don't put anything on the end, or if you put a comma 0, it'll assume that you are able to replace those numbers, and a comma 1 on the end will actually mean no replacement. Just a nice little quick way of generating some of your numbers if you get asked to do that within the exam. Okay, moving on to the next one. I'm not going to spend any time on this week, although some of these things will become important to us. But we touched on the whole distribution idea last week of generating things or using the normal PDF, normal CDF. So we might just skip over that one. And I've already pretty much talked about this slide as well, where we've got generate the following, 5 random numbers between 1 and 10, et cetera, et cetera. So again, we might just jump over that one straight away. Okay, in the next activity that I want to look at is the variability of the binomial distribution. Now, this leads nicely into something that Brian's going to do in a couple of more minutes, which is just touch on the central limit theorem. But to be able to generate in a spreadsheet and then be able to nicely graph the information. Now, I know that in this course, proportions is a very, very big part of the whole idea, and they'll be part of our end part of tonight's topic. But what I want to do to start with is just have a look at a couple of graphs and just get a feel for what our graphs are going to look like if we generate each of these types of numbers, and that again will lead nicely into the central limit theorem with Ryan. So I'm going to open up a new page, a sort of new problem in Doc, insert problem. I want to generate some numbers in the spreadsheet, so list and spreadsheet. I'll go up the top. I can call it X because I've started a new problem, so it won't have any problems with that. And I'm going to generate 50 samples, as it says in the question, of binomial distributions. So in data, data, random, binomial. We want 20 as our amount of outcomes, 0.2 as our probability of success, and let's say it's 50. If we press enter, at the moment we're just getting scores, and you'll notice that these scores are at the lower end, so again 0.2, 20% of 20 is around the 4 mark. If we graph these, so data and statistics, down the bottom, tab and then X, and what we should find is that we're getting a bit of a curve going on here, which again Brian will talk about very shortly, around about the 0.2, 0.3 mark of our out of 20. So we expect it to be around the 3, 4, 5 mark. If I go up to menu and do plot type, histogram, and we start to see a little bit of skewness there, but again, we're only on 50 trials. We probably expect, or 50 samples, we probably expect if we make those numbers a little bit larger, we might start to get a slightly different looking view of that. If we come in back into 2.1, the beauty of using the technology is not having to restart all that again, but going into our box, in our formula box, I'm now going to change that to 0.5. Now, out of 20 outcomes, 0.5 chances of success, we'd pretty much expect that should be 10 or around the 10 mark that's happening. It's going to ask you if you want to overwrite the data. Okay. And we'll find there's a couple of larger numbers and a couple of smaller numbers, but we see things hovering around that 10 successes out of our 20. If we come back to our graph, you'll notice that things have shifted over pretty nicely. If you go into menu, Windows, Zoom, and data, we actually notice that, again, this is now centering more around the 10 mark. So we're seeing that movement, that expectation, the variability of the binomial distribution, as we're changing our success value, the graph's moving accordingly. We'll have a look at the last one, so 0.8. We'd expect, again, this would probably be around the 16 mark. Override it, and if we come across and then menu, Windows, Zoom, and data, yeah, a little bit higher, but again, this is a random situation, so we're not expecting that we're going to get a perfect situation for 50 trials. Being 50 samples, we probably expect that it's starting to fit nicely and start to be a bit consistent, but we're getting roughly what we would expect, at least within the right region. As it says here, and what it might say within a test or exam kind of question on this kind of work, is to discuss this and maybe talk about it for different size samples and have a look at it from the point of view of different probabilities of success, looking at N being different, samples being different, and trying to bring that all together to see how it might connect together for the next bit of information, which is the central limit theorem. On that note, Brian, I might pass back to you because this is your moment of glory, and give you a chance to just talk the students through the central limit theorem based on some of the things that I've just explored.
Beaut, and they're possibly starting to recognise already in the shape of the graphs and the histograms that you're producing. They're probably guessing which way this is going. In fact, I hope they're more than guessing. I hope they are quite familiar with it, and this is just a lovely review for them. So I'm going to talk about larger samples, where the larger samples, I believe, are important. Now, this idea here we go, central limit theorem basically saying that if we have a large number of samples, then the distribution within that sample will approach a normal distribution. So what that really means in reality, it's probably easier understood through example. Let's say I will put up a list and spreadsheets here. Let's say I've got, I don't know, eagles. I'm going to call it eagles because let's say I just happen to know that statistically it has been determined that, shall we say, 60% of Western Australian maths method students are followers of the Eagles. Okay.
I think you'll find at the moment, Brian, there won't be a lot of people admitting to that, but we won't go any further.
Oh, mate, mine's the Tigers. So
very touchy subject over here at the moment, Brian.
Yeah.
But I'm a North Melbourne supporter, so I can't talk either. But yeah, sorry to interrupt. I just thought treading very delicate water there, Brian. But I'll let you use that one just for this example.
Just for the moment, okay. Let's say I took 100 such students. So I've got a sample of all of the Western Australian maths method students, and I took 100 of them. Now, it would be reasonable if I knew that 60%, or 60 out of 100, which of course is what percent means, Eagles supporters, then most likely I would expect that 60 people out of that 100 would be Eagles followers. Maybe it could be slightly less, it could be more. If I took lots of samples, let's say I took, 250 samples independently, then there would be some of those samples of which there would be very few Eagle supporters. There would be some samples where there's quite a lot. But they, I expect, would be in the minority. I still think most would cluster around the 60. So how I can set up an illustration for this using the lists and spreadsheet is in the definition for my column here in equals, I'm going to go into the statistics, and I'm going to go to distributions, and I've got hang on, I've got the wrong one. I want random binomial here.
Up in data.
Thank you. In the data, not in yep. So I'm in random binomial. So the list that we did here, so I've got, first of all, and as Stephen said before, it's the syntax that's important. So the first one is the size of my sample. So I've got 100 students in my sample. The next one is the probability, 60% or 0.6, that any individual would be an Eagle supporter, and then the number of samples. Now I'm going for a large number of samples here, 250. So what's likely to happen is that my grouping will approach, according to the central limit theorem, it's going to start approaching a normal distribution. And you see the values here. They're generally, 59, 60. Okay, there's some that are a bit higher, or there's one that's considerably higher. Do we have a sample that's considerably lower? If we keep looking through our list, here we have 48. So to get a bit of a picture of what that looks like, let's look at a picture of the data, and we've done this a fair bit already now, looking at pictures of data. And here are my Eagles. So I've got a dot plot. And so you see most are clustering around the 60. And on the outer edges, the lower numbers, and out of the higher edges, the higher. And I can change that from a dot plot using plot type to histogram. And so here we have it. And once it's in a histogram form, I can analyze it by showing a normal probability density function against that. So here it is. And so it's telling me that the mean of our sample, of our groups of samples, I should say, our 250 samples, is 59.6, which is about what I was expecting. I was expecting that it would be close to 60 out of every 100, or 60%. And this is handy here. This is the, so so this is the standard deviation being 4.87. Okay? So the bottom line is most of the data will cluster around that, and you know the proportions for 68% will be within, will be 4.87 higher or lower than 59.6. I expect 68% of the data to fall within that. There will be some that are very low and some that are very high. Stephen, have I got time to just give one more example of this?
Yeah, sure, Brian. That's fine.
Where I've read bits of this before, and it really drives home the idea, where there's perhaps an illness, and let's say that medically, where we know that of a particular illness that affects maybe 2% of the population. So it's not a large percentage, but it's probably not going to be great for you if you're in that 2%. But if it's 2% of the population, then two out of every 100 people. And let's say I'm looking at a town that has a population of 1,000. That's about the population of the town I live in fact. And so what I'm going to do now is I'm going to once again set this up for equals data and random binomial. I'm going to say that I have a sample size of 1,000, so it's 1,000 people living in a town about the size of Yackandandah, let's say. And the probability of this illness is 0.02, so 2%. And let's do this. There's many towns across Australia that are about the size of Yackandandah. Let's take a look at 2,500 such towns. Okay, I've chosen that number because that is actually what this spreadsheet goes up to, and we'll just sort of wait a moment because we've just asked the calculator to do quite a lot of calculation there, and I'm waiting for it to respond. It does take about 20 to 30 seconds, and it's pasted those values in. And so this could be town number 1 with 18 such people afflicted by that illness. This town's done quite well, only 15. We expect about 20, do we not? Okay? And that's about what's happening as I flick through the data. Now, what becomes rather unpalatable and difficult for people to understand is, okay, if I'm in the town that's with 15 people affected by this illness, well, yeah, okay, we're doing better than the national average. But what about the town that has so many more? So what I'm going to do now is I'm just going to sort under actions. I'm just going to sort the data, and it will override those values because it will place them in different places. So the data can be sorted ascending, yep, data of column B. And again, this is going to take a while. We've asked the calculator to do quite a lot of work. But the interesting thing is we often pick up newspapers or we see television reports of a particular affliction that's hit a particular area. This area has got twice the national average of a particular illness, shall we say. And people are upset by that, and understandably so. And they start to ask questions. Why is this the case? Why are we so far above the national average? And of course, we're testing the water. We're testing the power supply. Are we too close to that nuclear waste dump that's around the corner? And so these various things are questioned because it's hard for people to accept. And if a statistician comes along and says, well, sorry guys, what's actually happening is that you're just simply at that tail, you're at that end of a normal distribution curve. It is normal that someone is in that, and here we go, it is normal that somebody has those figures, even though we expect, so expectation is 20 per 1,000, i.e. 2%, but here you see I've got a town that has only 5 people afflicted by that illness, or 7 or 8. But what about at the other end of the show? See, most of them will be around the 20. But at the top end, 37. That's nearly twice the national average. So I just think that's a good illustration. I remember reading about that sort of argument years ago in discussions of statistics, and I thought, well, yeah, that kind of does help put things into perspective. There it is. And of course we can do the same deal, putting it into a histogram and putting the PDF over it. So there we have it. The mean, 99.97, which is about what we would expect. We were expecting 20, and the standard deviation 4.46. So that this fellow here, this town of 37, that was well above. That's quite a few standard deviations above the mean, but it does happen. It is normal, hence the term. So, Stephen, I'm hoping that helps put all that into context. Shall I send this back your way?
That sounds very good, Brian. Thank you very much. And one of the things that's very important to understand, especially now heading away from, and this is probably more for the teachers. I'm aware there's a few teachers out there watching, that we're probably getting away more from the idea of using numbers and now getting more into proportions with the central limit theorem. The old course was very heavy on the idea of looking at raw data. The specialist course still is doing a lot of that, so finding, if for any of those students out there who might be doing specialists, finding the mean of data is still a very big part of the central limit theorem. But for the methods course, very much heading into the proportions idea, which is leads nicely into the next little activity I'm going to look at. So the very nice generation of what Brian's done there with the raw data gives you an idea of your shapes. And again, your teachers would have spent a lot of time with you going through putting the proportions into the central limit theorem, looking at standard deviations and your means and looking at the connections there. One thing that I have noticed, and did a fair bit of searching on this is something that is mentioned in the syllabus document, but not many textbooks are actually covering it. There is one here in WA that's got it in it, but there's a number of, I've had a look in a lot of the Victorian, New South Wales and some of the other WA textbooks. It's covered in the syllabus, and that's this idea of the probability distribution of this very nice looking little rule here. Now, this rule talks about considering a certain amount of samples, so we might say it's B samples or C samples, whatever number we want to call it, each with n observations of a random variable x. Excuse me. And what we're doing is letting the proportion of the required attribute be P, so we're sucking into our point estimates and looking at what either the population proportion might be, or we might have to do a point estimate, which we'll get into in one of our last slides. For each sample, the sample proportion can be calculated, so we can actually work out the sample proportion, and this particular statistic can be generated. And we end up, what we can do is do this for each individual sample, and we end up with a distribution of this particular calculation. Now, this particular calculation might look a little bit familiar to those of you, or should look very familiar to you, in terms of in a different format. And that different format is our standard normal formula, where we have our z-scores, where we talk about the score, take the mean, so in this case our sample proportion is our score, take the mean or the proportion for the population, or it could be a point estimate that we're working with, and then this bottom thing is our standard deviation. So what it ends up doing is we expect it to generate over a series of different sequence samples a graph that ends up looking like a normal distribution, and we're hoping that it should end up having a mean of 0 and a standard deviation of 1. Now, not many activities out there, so I've come up with my own little way of showing this to my students, which they found was pretty good. You'll also notice there's some parameters here, again, just talking about, by the way, what will make this more normal, or make it fit in with the standard normal. The n is greater than or equal to 30 is a pretty stock standard number that we talk about for our sample size here in WA. This one here, the NP is greater than 5 and N take P is greater than 5, N times Q is greater than 5, is one that is debatable. There's different textbooks that have their views on that one. But the main thing I want to focus on is just looking at this distribution and trying to work out a way that we can actually show it in a way that gives us that normality. So I'm going to come back into my calculator, and I'm again going to set up a new problem. So I'm going to look into insert and problem, and what I'm going to set up here is a spreadsheet. And what I want to do with this spreadsheet is come up with a way of showing that this will approach our normal distribution. So I'm going to do a list and spreadsheet. Again, because I've started afresh, I can go into X. I'm going to generate a series of random binomial values. So random binomial. And in this case, what I might do is I might make it 100, a sample size of 100. So, and then we're going to have 0.3 as being our probability of success, and we might want to do that for 50 samples. But because we want to change this into a proportion, what we can then do is divide by how big each of our samples are. So we're going to divide by 100. So if we now press enter, what you should find is we get all these fractional answers. Now again, probably not greatly useful for us, although they're nice exact values. So I'm going to go up to Doc, Settings and Status, and change that to Approximate. Make default, and we should get a whole lot of decimal answers. And a little bit like what Brian was just showing to you, you should see that they're hovering around our we expect as our population proportion, which is the 0.3 for success. Nice little variation going there, but generally not too bad. Now what we want to do is we want to actually graph that, and we want to see what that is going to look like and see if it fits in with this idea that I mentioned earlier, that this is sort of like it looks like your standard Z-score setup for a formula. So I'm going to call this next column P, just for something to call it. And then into the next cell, I'm actually not going to use your formula cell. I'm going to go into B1, because what I'm going to do in a moment is copy this down and make it generate new values depending on what cell we're actually in. So I'm going to put equals, and in the equals one, I want to put a fraction, and I'm going to make it A1, so I'm going to refer to the value in A1, take the population proportion, so in this case it's going to be 0.3 because that was our success. I'm going to come down to the next cell, I'm going to put a square root sign in there, and then a fraction, because again we need to now put in our standard deviation. Now our standard deviation is the sample proportion times 1 take the sample proportion over the size, which is in this case 100. Now if I press enter, I get the first value, but what I want to do is generate that all the way down the page. Now, I guess one thing to just explain this, because our population proportion was 0.3 and our first sample was 0.31, we are just slightly above our population proportion, so we'd expect an equivalent Z-score or an equivalent frequency score here of 0.2162. In other words, it's slightly above our expected probability, or sorry, our population proportion. Now what I want to do is I want to copy that down. Now one of the reasons why I've kept the amount of samples reasonably small here, with my classes I've done this for a lot larger sizes, is just for time. So I'm going to go into Menu, Data and Fill, and now I'm going to just cut that down all the way down to the bottom. Now I did 50 samples, so down to 50. If I press Enter, I now generate all my numbers, and again these are equivalent scores that look very similar to Z scores because again it's using the same principle. Now what I want to do is I actually want to see what the distribution of those these generated scores are. So we're sort of looking at a frequency distribution of these probabilities. So I'm going to create a new page, Data and Statistics. I'm going to make that. Now, I'm not going to use X because that was the original sample proportions. I want to look at what we've just generated, which was my P. Excuse me. Now, straight away, you should see something interesting across the bottom, -3, -2, -1, 0, 1, 2. So we're already getting, without even changing this into a histogram, we're starting to get our idea of our standard deviations either side of the mean for a standard normal curve. So if I now go up to Menu, Plot Type, excuse me, histogram. Moment, little bit scattered because of the fact that our bin sizes are fairly large in terms of what our columns are. So I'm just going to go into an open space here and go Control Menu, which is our right click. Change the bin settings to equal bin widths. I'm going to make each of them 1. I'm going to align this so where I want the first column to align to on its left side of -3.5. And if I press OK, now we probably want to get a better view of that, so we can either go Menu or Control and right click. I'll go into Menu, Windows Zoom and Data. And what we get there is our normal distribution. And what you'll find is it's actually very nicely centred on our 0. We've got our standard deviations of 1 either side, 2 either side, and 3 either side. And showing what Brian talked about earlier, if we go into Menu and Analyse, Show Normal PDF, and we're getting a reasonable bell curve there looking at our normal distribution. What you should also find that's going on there is if I made my amount of samples, so we went from 50 to, say, 100 or 200, we would start getting an even nicer representation of the information. So just a nice way to have a look at that, our probability distribution of these scores. So what we ultimately expect to happen is as the sample size gets bigger on the bottom, the standard deviations are going to get smaller, so we can actually come back into our 3.1 and start playing around with different sample sizes, etc. So I might actually just change the 100 to 200. This won't make a lot of difference, and our number on the bottom 200. I'll still have 50 samples. If I press Enter, OK, come back into our 3.2, and you'll find that, as we'd expect, our standard deviation is getting smaller, so our curve is starting to get a little bit thinner. If I come into our Zoom and Data, we're getting a bit more symmetry going on, and particularly this is showing nicely the fact that we have our standard deviation getting smaller, so our graph is actually getting thinner. We can change things like our frequencies to be relative frequencies, etc., etc. But again, this gives you the idea of how we can actually represent that very, very nicely. Okay, I might move on. We've got one last activity I just wanted to spend time on, and that's the confidence intervals using your calculator rather than going through the whole idea of using the graphing idea and having to do it that way. There is actually a nice little quick template that we can use for a question like this. So, of a random sample of 500 voters in a particular electorate, 230 indicated that they would vote for the Julian party at the next election. And the way things are going in politics, I might have to start that. Brian, what do you reckon? The Julian party?
Oh, you got my vote, mate.
Find a point estimate for P using this random sample. So I guess we haven't had much interaction tonight, and I know that we're sort of into our last 10 or 15 minutes, but I'd just like any of the participants out there to just quickly enter in what they think the point estimate for this particular question might be. So I'll get you to have a watch of that for me, Brian, if you can, and our other helpers out there in Teacherland who are helping out tonight. So we're looking for the point estimate for this particular question.
Bring me some thinking music. Yeah,
I was actually thinking of doing that for one of the first sessions, but I thought I might get in trouble copyright-wise. I might have had a few people from above come down on me very heavily, so I thought I'd better not go for some Love Me Do or a bit of Beatles music or a bit of Billy Joel, so might even get in trouble for even mentioning their names on the internet, so I'll probably be quiet now. Okay, getting any answers through, Brian?
No, fairly quiet so far.
Okay. Well, I'll give people another 10 seconds. Shouldn't take too long. So we're just looking for a point estimate for P using this random sample. I think we're missing a couple of our normally very good answerers. I know we've got some very good people out there who have been on every week. I'll get straight. I'll move on because I again do want to show a couple of more things. So if we are going to look at our point estimate, what we're doing here is we don't know the population proportion, so we're going to use a point estimate to estimate the p-value. So in this case, that would be 230 over 500. So all we're doing really is looking at the amount of positive outcomes out of our total sample size. Excuse me. And so we'd expect that to be 230 over 500. Word of advice to students out there, I probably wouldn't worry about simplifying that fraction for two reasons. One, in the exams, they're not going to expect you to do too much simplifying of fractions. But secondly, when we get to the entering of the next part, it's important that we actually keep the sizes of our samples very clear for our entry, which is part B. Find a 92% confidence interval for the proportion of Julian voters, P, in the electorate. So we're going to come up into menu. And, whoops, probably would help if I actually went into a calculator page, so we might just do that. So doc, insert, new problem, and a calculator page. Now I'm going to go into menu, statistics. Now this time we're moving away from the probability option and we're looking at statistics. And you'll notice down here, number 6 is confidence intervals. And the one we're going to use is number 5, 1 prop Z intervals, which is basically using the information to come up with our confidence intervals for this particular data. Now the successes of X, that's 230 in this case. Excuse me, 500 for our N value, which is our sample size. And in this case, our confidence level is 0.92. Now, I know my students have asked me a lot, do they need to remember all these things? It's important that you do know how to generate different confidence values other than just the usual stock standard ones in the textbook. If you've got the ability to use your calculator here, it'll do a lot of the work for you. Then if we go OK, and what we should find is that our confidence interval comes up straight away, that we have 0.42 as our lower value, around about 0.5 for our upper value, and then our sample proportion is 0.46, which is nicely in the middle, so it shows that symmetry. It's got our margin of error, and it tells us our N value. Now, the next part actually says what would happen if it suddenly went to 5,000 and 2,300. I've used this one a few times with my students just to illustrate the importance of simplifying fractions can cause problems here because this looks like basically the same fraction. But in this case, we have a larger amount of voters. So if we go menu, statistics, confidence intervals, 1 prop Z interval, 2,300, 5,000, 0.92, make sure that you do remember to put that in as a decimal, and then OK. And what we should find now is that our confidence interval is 0.45, our upper limit is 0.47. You'll notice that our sample proportion is still the same, it's still in the middle, but our actual interval's got smaller. And that's because now we've got more, the sample size is much bigger. We've got a bit more confidence to know that our population proportion would fall somewhere within those boundaries. Our margin of error is much smaller, and it will again show you your sample size of 5,000. So comparing your answers in C and D on the next slide, again, you can see that as the sample size gets bigger, our confidence interval is actually getting smaller because we don't need such a big boundary to feel confident that our values are going to fall within those limits. I might leave the last part. I'm fairly confident that students have actually seen a lot of this stuff before, so particularly this one, maybe not the shortcuts because, again, a lot of times you might have used the graph, but determining the sample size using margins of error, I normally just use solve for that, so I'm hoping, again, that you may have gone through that. If you have any questions or whatever, feel free to send messages through the emails or through your teachers. A lot of them have my details already. I'm quite happy to talk about a few shortcuts and tricks if people would like that. On that note, there were, as per usual, always every week, Brian, there's lots of things I'd love to go through, extras, but I think time's actually catching up with us again. And I noticed we've got about 5 minutes to go, and I know being our last session together, that you had a few things that you just wanted to talk about. So I think I might pass back over to you, Brian.
Okay, and of course the main one, of course, is big thanks to you, Stephen, for running us through the program. and I think it's just been a beautifully balanced coverage of the main points of the course, and for students to have the opportunity at this stage of the year to once a week for 5 weeks, basically in 5 hours, to review pretty much the essential points of the whole course is, I think, very well worthwhile. So thank you for that, and I know you've put a lot of work and preparation into the PowerPoints and the TNS files and the activities that you've chosen to do. And we will hopefully see all that reflected in some great... Yeah, terrific, mate. And as always, a pleasure to be working with you.
Yeah, always.
I just thought I'd finish with a couple of things here. We had some students asking about coding earlier on, and it's not really in the Maths Methods course, but there is heaps certainly that can be done on coding on the calculators. Look, guys, wait until after your exams, because what's going to happen, this is highly addictive, this stuff. You get into it and there's a program called 10 Minutes of Coding. Within 10 minutes, you're hooked and you want to be doing more and more of it. This is the American website that I'm showing you here, where there's a little device called the Innovator, which is like some other instruments that you may have seen before that can be connected to computers and programmed from computers. You can have motors and lights and buzzers and so forth, and also sensors. You can put in temperature sensors and oxygen sensors and pH meters and so forth. So that's the device there. And if you want to learn about the coding for a start, this is the Australian website, which you've seen a few times now. There's the link to your program, which has been a really good one. And you see that you're among only 2 states where there's really been a focus on some of the support for exam preparation. And if you wish, you might even, some of this, like the Maths Methods from the Victorian side of things, you might even want to look at as well. But of course, following your link, you see all these on the YouTube. But just back to the main one here. This link here, this TI codes, this is the link through to the coding, just in answer to those students who have asked about coding and wanting to get more involved in that. I won't show much more of that for now.